Okay, we're going to talk about section 2.1, which is the basics of functions and their graphs, and section 1.1, which is graphs and graphing utilities. I like to teach the two sections together because they go together very well. The material is similar enough to put them together, and there's a lot of overlap between the two. So the first thing that we need to look about in these two sections is the idea of a relation. And what a relation is. Now, I'm not talking about relations like aunts, uncles, and brothers and sisters. I'm not talking about relationships like boyfriend-girlfriend relationships. I'm talking about mathematical relationships. And mathematical relations are simply sets of ordered pairs. Now, you've seen ordered pairs. You know what they look like. You've got parentheses here, a comma here, and you know that we typically put an x value in here and a y value in here. That is a mathematical relationship. In other words, when x is this number, y will be this number. Or when y is this particular number, x will be this particular number. And that relationship is established based on what the equation or the function may look like. So that's what a relation is, just simply a whole bunch of ordered pairs. Now, once you've established that you have a relation, there are two parts to that relation. You've got your domain and you've got your range. Domain is input. It is what you're putting into your relation. And typically, which of these variables do we put numbers into? Yeah, that's typically your x variable. So usually, your domain is going to be your x variable within your relationship. Now, the good, exact, mathematical, nice definition of a domain is that it's the set of values that are allowable substitutions for the independent variable. In other words, it's the numbers that you can put into your relation, into your equation. And that's why, like I said, typically we put into the x variable, and that's why your domain is considered your input. It's what you're putting into it. And what is allowed to be put into it. Now, we'll look at that in a little bit later, so it'll make more sense. But the idea of what's allowed and what's not allowed to go into it. But this idea of the independent variable, an independent variable is going to be the variable in an equation that can be assigned any value. So in other words, this idea of your independent variable, your domain, and your input, that's all kind of talking about the same stuff. It's all saying, what can I put into this equation? What can I put into this relationship? And that's what your domain is. Now, a range, if your domain is your input, then what would your range be? Exactly, it's going to be output. Now, I've told you many, many times that mathematicians are not creative. We call it like we see it. And this is the one time where I felt like input and output were perfectly good words. Why did they create domain and range? I have no clue. Input and output were perfectly fine. But anyways, your range is going to be your output. So if you put in for your x, what variable typically do numbers come out of? Yes, that would be your y variable. So your range is typically going to be your y variable in this case. The really good definition of your range is going to be it's the set of values that result from the substitutions for that independent variable. And that makes sense. If my domain is everything that I'm putting into it, then what's the result? What comes out of it? That's going to be your range. Now, that leaves us to the idea of a dependent variable. So we have an independent variable that's going to be your domain, and a dependent variable is going to typically be your y variable, but it isn't always the y variable. The good definition is that it's the variable in an equation that depends on the values that are assigned to that independent variable. Key being depends. Mathematicians now were not creative. So a dependent variable is going to depend on the other one. And oftentimes it's much easier to identify your dependent variable than it is to identify your independent variable. Me, frequently, I will look at my equation and I will say which one of these variables depends on the other one. That's my dependent variable. The other one has to be my independent variable. So it's much easier to identify your dependent variable than it is to identify your independent. So even if your directions say identify your independent variable and then your dependent variable, do your dependent first because it's much easier to identify. So again, what is happening here is that we've got the idea of a range and an output and a dependent variable. They're all kind of talking about the same thing. All of them are saying what's coming out of your equation, what's coming out of your function, so your output. And again, domain is going to be input, range is going to be output. Typically domain is X, but it doesn't have to be. Typically range is going to be your Y. Okay, so now we're going to talk about functions. A function is a special type of relation, and it's kind of like saying, okay, if you have a relationship, and let's say you're boyfriend-girlfriend, and you decide to take that relationship a step further, you become husband and wife. Then what you've done, because you've taken that a step further, is you've put more criteria on your relationship. You put more characteristics into your relationship by taking it a step further. So mathematically, we can do the same thing. In other words, you can have a relation that takes on new characteristics, more special characteristics, and if it does that, then we take a relation and we call it a function. So all functions are relations, definitely, but not all relations are functions. Only the relations that have a special characteristic are functions. So the definition of a function is, it's a relation, definitely, in which for each x value, there is one and only one y value. So let me give you a visual of what that would mean. Let's say I've got this machine here, and this machine, let's say that it is a relation machine, but I'm trying to decide, is this machine a function machine? So if it is a function machine, that means for every x value that I put in there, only one type of y value is going to come out. So let's say I put a cell phone into my machine, and then what happens is it produces a marker. Well, if this is a function machine, then that means that I'm going to put something else in there. I'm going to put a dry erase marker, or sorry, an eraser in, and then what happens is out comes a marker. This is a function machine. However, if I put a marker in and out comes a cell phone, but then I put a marker in again, and this time out comes an eraser, now my relation machine is not a function machine, because what I have done is I have got the same input going to two different outputs. And that is not a function when you have the same input going to two different outputs, something like this. If I've got two different outputs going to the same input, that is a function. Now, it is much easier to identify what is not a function as opposed to what is a function. Kind of like I said, it's easier to identify your dependent variable than it is your independent variable, kind of coming through the back door, doing a little bit backwards. Same thing here, it's easier to do it a little bit backwards and identify what's not a function as opposed to what is a function. So you need to burn this picture in your brain. If you have the same x going to two different y values, that is not a function. Burn that picture in your brain. Same x, two different y values, definitely not a function. Everything else is a function. Everything else is a function. So in other words, if I've got two different x's going to the same y value, that is a function, not a problem at all. If I've got the same x going to the same y, back and forth, back and forth, back and forth, then this also is a function. Like I said, it's easier to identify what is not a function than what is a function. Same x, two different y's. That is not a function, that's not okay. Everything else is. Now, once you've established that you do have a function, because this is a special type of relationship, we give it special notation. And so the notation then looks like this. Now, typically we're used to saying, okay, if something is inside of parentheses and something is right up against the parentheses, then that indicates multiplication. This actually does not indicate multiplication. We read this as f of x. So it is simply notation. It is not mathematical operation at all, just notation. But when you see f of x, what that means is you are going to substitute what is inside the parentheses you're going to substitute that for the x. Everywhere you see an x within that relationship, within that function, you're going to substitute what is inside the parentheses for that x. So whenever you have functions, you've got an x and you've got an f of x. Your f of x is acting like a y. it is a y. It's just we turn the y into this notation to say, hey, this one's special. This one has special characteristics. I'm not going to have any cases where the same input produces two different outputs, and because of that, I'm not going to call it y anymore. I'm now going to call it f of x. But it acts like a y. So if that's the case, let's identify which of these is the independent and which is the dependent variable. Remember, it's easier to identify your dependent variable first because it depends on the other one. So which of these two would depend on the other one? Absolutely. Your f of x is going to depend on whatever you're plugging in for the x. So your f of x is going to be your dependent variable, and that means that your x, the one left over, has to be your independent variable. So now that we know how to recognize that we have a function, let's take a look at what it takes to evaluate the function. Recalling that this is an f of x, and recalling that whatever is inside the parentheses gets substituted for the x. So what we're going to do here is take this function and we're going to evaluate it for f of 2, f of negative 2, and f of negative x. So if I'm going to evaluate f of 2, what that means is I'm just simply going to take this 2 and I'm going to plug it everywhere I see an x. And then I'm just going to follow order of operations. So in other words, I'll have 4 times 2 to the third power plus 1 over 2 to the third power. So then, once I plug it in, all I have to do is follow order of operations. And PEMDAS says do what's inside the parentheses first, but there's just a single number in there, and do your exponents next. So 2 to the third power is going to be 8. These are sitting beside each other. That indicates multiplication. And 2 to the third power is 8. Multiplication and division comes next. So 4 times 8 is going to be 32. And now I'm going to do the additional on top on the numerator, and I'll get a 33 over 8. Remember, you don't need to worry about mixed numbers. Just simplify fractions if you can. That one doesn't simplify, so there's my answer. So that's what f of 2 means. Now I'm going to do f of negative 2. And what a lot of people say is they go, well, if all I'm doing is changing the sign on this, then surely that just means I'm going to change the sign on the answer. Do you think that's the case? Well, let's find out. Let's plug it in there. So what I'm going to do again is put that negative 2 everywhere that I see an x, and then I'm just going to follow order of operations. So I'm plugging it in. Whoops, that's a negative 2, and that's a negative 2. Notice what I did here is I put the negative 2, the whole negative 2 is to the third power, not just the 2, but the negative as well. So it's very important that you understand that. So now I'm going to follow order of operations, which again says, let's do our exponents first. Negative 2 to the third means negative 2 times negative 2 times negative 2. Now 2 to the third we know is 8, but negative times negative is what? Absolutely, it's a negative. So I'm going to have 4 times a negative 8 in this case. And that means on the denominator, I'm going to have a negative 8, because yet again, negative 2 to the third power is negative 8. Multiplication comes next in PEMDAS, so 4 times negative 8 is going to be a negative 32. And like we did before, we're going to add up on that numerator, getting a negative 31 over a negative 8. And yet again, just simplify if you can. Well, I know that a negative divided by a negative is a positive, but I also know that 31 over 8 does not simplify, and that's as good as that one gets. So that's what happens whenever you evaluate f of negative 2. Now the last one says, let's do f of negative x. So that's a strange concept. To say, well, what I'm going to do is I'm going to take that x out of there and I'm going to put a negative x in its place. Why on earth would we do something like that? Well, much later in the semester, we'll see the value of doing this. Right now, it's just an exercise in being able to plug it in and then see what happens because of following order of operations. So order of operations says do those exponents first, and we know that x to the third is just an x to the third, so this really is an issue with this negative. Negative times negative times negative is negative. So we wind up with a negative 4x to the third here, because ultimately, let me step back here, ultimately it's 4 times a negative x to the third. And the same thing down here, this ends up as a negative x to the third. Now, 4 times the negative x to the third is a negative 4x to the third plus 1 over a negative x to the third. At that point, the only thing that we a lot of times do is just having that negative in the denominator is loosely said bad notation. Typically, you don't see a negative in the denominator. So how would you fix that? Sure, you would multiply your denominator by a negative, but remember when you multiply a denominator by a negative, you also need to multiply the numerator by a negative as well. So what I'm going to do here is I'm going to multiply this entire numerator by a negative, and I'm going to multiply my denominator by a negative. When I do that, essentially what happens? Sure, I'm just going to change all those signs. So that negative 4x to the third becomes positive, the 1 becomes negative, but the beauty is this denominator now becomes positive. And so that's what I've got. Don't worry about taking this and dividing it out. You could divide the front terms, but then you'd also divide the back terms as well, and it's just not necessary. You do go ahead and clear out the negative that's in the denominator, but you don't need to go any further than that. So this is what happens whenever you need to evaluate functions. Okay, so now let's take a look at being able to graph our equations. There's 3 methods for graphing equations, and we're just going to take a look at the first one for now, which is the point plotting method. But before we get into that, we need to understand what a graph of an equation actually is and what it means. The graph of an equation in 2 variables is the set of all points whose coordinates satisfy the equation. In other words, whenever you get those points, and remember points come as coordinates, and you'll have your x coordinate and your accompanying y coordinate because of the relationship. What that means is when I put this x value into the equation, this is the only y value that will also accommodate the equation and make a true statement. So these points here will satisfy the equation and make it a true statement. So in other words, when I join all of those points together and connect them either with a straight line or a smooth curve, when I connect all of them, everything that is on that line, on that curve, on that graph, all of them will satisfy the equation. Anything that is not on that curve will not satisfy the equation. Understanding that satisfying the equation makes the equation true, keeping that pan balance idea in mind that the left and the right side are going to be the same. Very important that you understand what the graph of an equation actually is. It is a picture representation of everything that will work in the equation. So let's take a look at what this point plotting method looks like. I've got an example here. My equation says y equals x to the third plus 4, and I want to graph it using that point plotting method. What point plotting does is it says, okay, let's pick some values for x. Since x is my domain, my input, let's put those things in there and let's see what spits out for the y value. So I'm going to just pick anything that I want for the x, but the directions here say, let's limit this to integers. Integers leaves out what types of numbers? Yeah, leaves out fractions and decimals. So I'm going to leave out fractions and decimals. I'm going to start with a -3 and I'm going to end with a +3. So the directions here have kind of limited me on what I can use in order to put into my function and be my domain. So what I'm going to do is I'm going to say, I'm going to make a table here, and in that table I'm going to start with a -3 for my x. I'm going to go to a -2, a -1, a 0, a 1, a 2, and a 3, leaving out the fractions and decimals. Now what this means is, this is my domain, I'm going to put that into this function everywhere that I see that x. So here's what the function looks like, x to the third plus 4. I'm going to take that -3, I'm going to put it in there, and then I'm going to follow order of operations. Order of operations says let's do the exponents first. So -3 to the third power is a -27. -27 plus 4 is going to be a -23. That is my output. That is my y value. So that establishes a relationship, like I said before. The relationship says, okay, when the x is a -3, in this case, because of this function, the y is going to be a -23. And then I'm just going to keep on doing that. So I'm going to try out that -2, and I'm going to put it inside the function everywhere that I see the x, and I'm going to follow order of operations, which says do the exponents first. So -2 to the third is a -8, -8 plus 4 is a -4. So that establishes a new, not a new relationship, but it says that, okay, and because of this relation, when the x is a -2, the y is a -4. And I'm going to keep on going, and I'm going to put that -1 in there and do the same stuff. -1 to the third is a -1, -1 plus 4 is a 3. So now it's establishing that when the x is a -1, the y is a 3. Again, because of that relation. Now I'm going to try the 0 out. And following order of operations, 0 to the third power is 0, 0 plus 4 is 4. The relation says that when x is a 0, the y is a 4. Now I'm going to go to the positive numbers, and like we saw before, a lot of people will say, well, if I'm just changing the exponent, then that's just going to change this number here, and where it was positive, now I'm going to make it negative. We saw that that might not necessarily be the case. So I'm going to plug the number in and follow order of operations. 1 to the third is 1, 1 plus 4 is 5. Sure enough, it doesn't just change the sign of the answer. So now I'm going to put the 2 in there and follow the order of operations. 2 to the third is 8, 8 plus 4 is 12. So my relation is that when x is 2, y is a 12. And the last one, I'm going to put the 3 in there. 3 to the third is 27, 27 plus 4 is a 31. So the relation is that when x is a 3, y is a 31. So now I've got all these ordered pairs, and you know that when you have ordered pairs, you can put them on the 2D coordinate plane and you can graph them. So I'm going to graph my -3, -23, which is sitting way down here somewhere. I don't have a big enough graph for that. But -2, -4, I certainly can put on the graph right there. -1, 3 sits right here. 0, 4 sits right here. 1, 5 sits here. 2, 12 is going to sit up here a little bit. And then 3, 31 is also off the charts up there. It didn't make my graph big enough. But now I can connect them. And when I do, it's going to look sort of kind of like this, making a little bit of a Nike swoosh. And incidentally, I know that's going to happen because anytime I have a third power, which is called a cubic, we looked at that when we classified our polynomials, cubics typically make that little Nike swoosh pattern, which is not something you have to know, but it is important to note there that this is what happens whenever you do your graphing by point plotting method. All point plotting does is it says, pick some values for x, put them into that function, see what spits out, create ordered pairs, put the ordered pairs on the graph and connect them. So let's try another one then. This time I've got an absolute value function, but my directions are the same, and they say, let's do this by point plotting. Same directions say that let's start with a -3 and end with a +3, leaving out all those fractions and decimals because I'm going to use integers. So point plotting says, okay, let's make our table, let's put these values into that function, see what spits out. So I'm going to take my -3 and put it into that function, which says I'm going to take a -3 times the absolute value of that x plus a 9. Now, absolute value, you know that does mean distance from 0, and so basically it just makes it positive. But it also kind of acts like a grouping symbol in the sense of we've got to do absolute value before we do the multiplication. So absolute value of -3 is +3, but then this -3 times the +3 is a -9. -9 plus 0 will give, -9 plus 9 will give me a 0. So the relationship that has been established is that when the x is a -3, the y is a 0. So we'll try it again. This time let's put the -2 in that absolute value. And so when I put a -2 in there, once again, do the absolute value part first. The absolute value of -2 is 2. 2 times -3 is a -6. -6 plus 9 will give me a +3. So the relationship established there is when x is a -2, y is a 3. And keep it going. So this time what I'm going to do is I'm going to put my -1 into the absolute value. And the absolute value of -1 is 1. 1 times a -3 is a -3. -3 plus 9 will give me a 6. So the relationship is that when x is -1, y is a 6. And I'll keep on going. This time I'm going to put a 0 in the absolute value. Absolute value of 0 is 0. 0 times -3 is 0. 0 plus 9 will give me a 9. And so the relationship is when x is 0, y is a 9. Keep it going here. So I'm going to put my +1 into the absolute value, which the absolute value of +1 is 1. 1 times -3 is -3. -3 plus 9 is 6. Relationship is that when x is 1, y is 6. And a couple more times. Pop that +2 in there. And the absolute value of +2 is 2. 2 times -3 is -6. -6 plus 9 is 3. Relationship is that when x is 2, y is 3. Are you noticing something here? Yeah. I'm going from 0 to 3 to 6 to 9, back down to 6, back down to 3. So probably what is this going to be? Let's see if it is a 0. So I'm going to throw my +3 in here. Absolute value of +3 is 3. 3 times -3 is -9. -9 plus 0, yep. -9 plus 9 is 0. I did it again. So when my x is 3, my y is 0. And just like in the last one, now I've got all these ordered pairs that I can put on my graph. So So negative 3, 0 sits here, negative 2, 3 sits here, negative 1, 6 sits right up here, 0, 9, 6, 7, 8, 9, pretend it's straight, 0, 9 sits right here, 1, 6 sits here, 2, 3, oops, 2, 3 right here, and 3, 0 right here, and I can connect them. Notice that when I connect them, first off, I can't make a straight line to save my life, but it should be straight. More than that, notice that I'm not connecting it with a curve up here. It is a sharp peak. That is because it's an absolute value function. Absolute value always makes a V, whether the V go down or whether the V go up. But that's what happens with absolute value, which again, that's not so much the point of the lesson. The point of the lesson is to be able to graph using your point plotting method. Okay, so now that we've got the method of point plotting down, let's take a look at certain features of the graphs. One of the most important features of the graph is going to be where it crosses your x-axis and where it crosses your y-axis, which is what we call the x-intercept and the y-intercept. Mathematicians are not creative people at all. We call it like we see it. So an x-intercept is going to be where the graph intercepts. I think of it as like a football interception, where the quarterback is passing the ball to his wide receiver, but the safety comes in and crosses the path of that ball, and because the safety crosses the path of the ball, the safety catches the ball, which is the defensive player, and so therefore what we call that is an interception. The only way that the interception could happen would be if that safety crossed that path of the ball. If the safety's way over here and the path of the ball is like this, safety cannot make the interception. The only way it's going to happen is for the safety to cross that path. Same thing here in math. So an x-intercept is going to be the point where the graph crosses the x-axis. And again, mathematicians are not creative, so x-intercept is where it crosses the x-axis. On the flip side then, same token, the y-intercept is going to be where the graph crosses the y-axis. Again, the idea of an interception or an intersect, same concept here. So if I'm thinking about an x-intercept, and let's put the 2D coordinate plane up here so we can get a visual of what's happening. If it's going to cross this x-axis right here, what do you know about every single point on this x-axis, every one of these points? Notice that with every one of them, there is no up or down movement at all on this y-axis. Therefore, when I think of its coordinates, when I think of this y-coordinate right here, what do you know about every one of these y-coordinates? Sure, every single one of them is going to be 0. So when I think about the coordinates for an x-intercept, I guarantee that the y-coordinate is going to be 0. My x-coordinate can be absolutely anything. It can be positive, it can be negative, fraction, decimal, irrational number, anything at all. But what I do know for certain is that the y-coordinate is definitely going to be a 0. Now, because of that, oftentimes we call our x-intercepts zeros. Now, on the flip side, with your y-intercept, what happens there is, let's take a look at our y-axis. And on this y-axis, if it's a y-intercept, then that means it's crossing this axis right here. Now, on this axis, what do you know about every one of these points going through here? What do you notice? Yeah, every one of them has no left or right movement at all. Left or right movement is going to be along this x-axis, so that's going to be the x-coordinate. So what happens here whenever you have a y-intercept, because there's no movement, that means your x-coordinate is going to be 0. So my coordinate for my y-intercept is, let's make the x 0. Y can be anything. It could be positive, it could be negative, fraction, decimal, irrational number. But my x-coordinate will definitely be a 0 whenever I have an a y-intercept. So let's take that idea here and let's practice this a little bit. So far we've talked about whether or not you have a function. We've talked about domain and range. We've talked about x and y intercepts. So I've got an example here where I have this relation. Remember, relation is simply a set of ordered pairs. So I have a set of ordered pairs here. And what I need to do is, first off, I need to decide whether or not this thing is a function. Now remember, burn this picture in your brain. When I have the same x going to 2 different y values, is that a function or not a function? Definitely not a function. So I need to look at these string of ordered pairs and I need to see, is there a case where I have the same x going to 2 different y values? And what I notice in here as I look at this relation is I've got an x of -7, an x of 3, 0, -2, 6, -6, 4. They all have none of them even have the same x. So there's not possible to have the same x going to two different y values. This is not a function, so in this case, yes, this definitely is a function. I do not have any repeated x's. Now I need to look and figure out what's the domain in this thing. Remember, domain is your input. It's your x coordinates. So when I list my domain, this is going to be a set of numbers. And I'm simply going to list all my x values, starting with the lowest number, the smallest number, and then finishing off with the highest number. So my domain is going to be, my lowest number is -7, then it comes up to the -6, and then it goes to a -2, and then it goes to a 0, and then it goes to a 3, and then it goes to a 4, and then finally to a 6. So that's going to be my domain, the -6, -7, -6, -2, 0, 3, 4, and 6. My range is going to be all the y values. So I'm going to do the very same thing here. This is going to be a set of numbers, and I'm going to list all the y coordinates, starting from the smallest and going up to the highest. So the smallest y value that I see is a -4, and then the next y value that, -9, my apologies. There's one smaller than that. Then the -4. Then I'm going to go to a 0, and then I'm going to go to a 4, and then I'm going to go to a 5. Now notice the 5, there are 2 of these. I don't need to list them twice. You only need to list it once, because we don't care how many times it shows up, just that it does show up. So I'm going to only list the 5 once, and then finally the 20. So there's my range. This is all of the outputs, all of the numbers that will come out when these numbers are put into the function. So now I simply need to list my x-intercepts and my y-intercepts. X-intercept, remember, that's where it crosses the x-axis, and anything on this x-axis right here has no up or down movement at all, which means their y-coordinate's going to be 0. So I look at all these ordered pairs and I figure out which one has a y-coordinate of 0. That's this one right here. So my x-intercept is going to be -2, 0. Now what I'm going to do is try to figure out my y-intercept, and the y-intercept, remember, is where it crosses this y-axis that you see right here. On this y-axis, there's no left or right movement at all. So therefore, that means that my x-coordinate is going to be 0. So I look at my ordered pairs and figure out which one has an x-coordinate of 0. That's this one. And so my y-intercept is going to be 0, 5. So that's how you figure out, when you have a string of ordered pairs, whether or not you have a function, what your domain is, what your range is, and what your x and y intercepts are. So let's practice another one. So in this time, with this string of ordered pairs that we know is a relation because it is a set of ordered pairs, I'm trying to decide whether or not it's a function. Remembering that I've got this picture burned in my brain, and what this means is when I have the same x going to 2 different y values, it is not a function. So do I see a situation where I have the same x going to 2 different y values? Right here, this is an x of 2. Here's another x of 2. But notice that this x of 2 is going to a -1. This x of 2 is going to a 7. So I do have the same x going to 2 different y values. Therefore, is it a function or not a function? Absolutely right. That is not a function. So now, even though it's not a function, it's still a relation. It's still a set of ordered pairs. Therefore, I can identify a domain, a range, an x, and a y-intercept. So let's take a look at this idea of a domain. Domain, remember, is your x's. So I'm going to look at all of these ordered pairs, and I'm just going to figure out, okay, what x's are listed there, starting with the smallest and going to the largest. So the smallest x I see is a -8, and then the next one's a -4, and then the next one's a -3, on up to a 2. And remember, I don't care how many times it shows up, just that it does. So I'm only going to list that 2 once. And then I'm going to go up to a 4, and then on up to a 9. And so that is going to be my domain, all of the x values that are listed there. Now I'm going to do my range, and with my range, similar idea here, but instead I'm going to look at the y coordinates. So what I'm going to do is I'm going to start with the smallest y value that I see, which is going to be a -5. And then the next highest y value is a -2, and then a -1, and then a 0, and then on up to a 6, and then on up to a 7, and then on up to an 8. And so there's my range, all of the y values that are included in that string of ordered pairs. So now I just identify my x and y intercepts, keeping in mind x-intercept, yet again, here's that x-axis, and x-intercept is where it crosses that axis. There is no up or down movement at all, which means I need to find where the y-coordinate is 0. So as I look at these ordered pairs, where is the y-coordinate 0? Yeah, right on that one. So there is my x-intercept of -8, 0. Now I need to figure out my y-intercept, and so y-intercept is where it crosses this y-axis. That y-axis has no left or right movement at all. So with no left or right movement, that means let's make the x-coordinate 0. So as I look at my ordered pairs, I'm looking for the one that has an x-coordinate of 0, and I don't see one. So what am I going to do? Well, it's okay to not have one of those intercepts. You have to remember what the definition says. The definition says an x-intercept is where it crosses the x-axis, meaning make the y 0, and the y-intercept is where it crosses the y-axis, meaning make the x 0. So if you don't see that happening, that means you do not have that particular intercept, and it's okay for that to happen. So that's how you, again, another example of taking a string of ordered pairs, figuring out whether or not it's a function, identifying the domain, the range, and the x and the y intercepts. Okay, so now what we're going to do is we're going to take a look at some graphs, some pictures, and do the same thing that we did before with the list of ordered pairs, but this time we're going to take the picture and we're going to determine whether or not it's a function, determine the domain, the range, the x-intercepts, and the y-intercepts. Now, determining whether or not it's a function is not going to be any easier or any harder than whenever you had a string of ordered pairs. It's just different. I need to keep in mind that what I'm looking for is when the same x goes to two different y values. When that happens, I do not have a function. So if I look at this first picture, this first graph, notice what's happening here is this x of a -4 comes down to a value of -3. This x of -2 comes up to a value of 2. This x of -1 comes up to a value of 3. This x of 0 comes up to a 1. This x of 2 comes up to a 3, and this x of 3 comes down to a -2. Now, granted, these two x values came to the same y value, but it's okay to have two different x's going to the same y. That's not a problem. I don't want the same x going to two different y's. So do I have any situation where any of these x's are going out to two different y's? No, I do not. So therefore, I'm not seeing this, and this means not a function. So yes, this picture definitely is a function. Now, take a look at this one. What happens in this one is I've got a situation where this x right here is coming up to this and down to that. Up to this that y value and down to this y value. I've also got a situation where this x is coming up to here and it's also going down to here. So I do have a situation where I have the same x going to two different y values. Therefore, this is definitely not a function. And if I take a look at this one, this x is sitting right here. This x comes down to this one. This x comes up to this one all the way up here. Do I have any situation where any of these x's are coming out to two different y values? I'm not seeing this happening, so therefore I can identify that yes, this one is a function as well. And on this one, similar idea. Are any of these x's here coming out to two different y values? That's not happening. I'm not seeing this picture, so this is definitely going to be a function as well. So what this does is it gives us a tool for being able to determine whether or not you have a function if you have a picture, or in other words, a graph of your equation. So to determine whether or not your graph is or isn't a function, what you do is you use the vertical line test. Because your vertical line test is based on this idea, this picture that I had told you about, where I've got the same x going to two different y values, and when that happens, I do not have a function. Because if you picture a graph, and let's take the second example we had looked at in those pictures, a graph that looked like this. What was happening there was I had this x here going up to this one and down to that one. We said that that was definitely not a function, because I had the same x going to two different y's. But this right here is essentially making a vertical line through that graph. So what happens whenever you use that vertical line test, oh, I'm sorry, use vertical line test. There we go. So what happens is you drop a vertical line through your graph. Your graph is not a function if it hits two or more times. Because if it hits two or more times, you have created this situation right here. The graph is a function if it hits once and only once. So that is how your vertical line test works. So we already identified these four graphs, whether or not they were functions or not. Let's see how the vertical line test would have made that a whole lot easier. Notice in this example that when I drop that vertical line, it hits once, twice, and remember, when it hits two or more times, it's not a function, so that definitely isn't. Notice in this one, drop a vertical line here, hits once. Drop a vertical line here, hits once. Here once, here once, here once. Okay, that one's a function. Notice the vertical line hits here once, here once, here once, here once. That also is a function. And even in this one, drop it through here, hits once. 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 Here once, here once. That one's also a function. So the vertical line test is very helpful in being able to identify whether or not you have a function. Quick and easy. Now remember, we also needed to determine whether or not we had domain, or not whether or not we had domain and range, but we needed to find the domain and range in each one of these. So let's take a look at this one for its domain. Remember, domain is going to be the x coordinates. So what I'm going to do here is I'm going to look at all the x coordinates. This x for this point is a -4, and for this point its x coordinate is a -2. For this point its x coordinate is a -1. For this point its x coordinate is 0. For this point its x coordinate is 2. And for this point its x coordinate is 3. So there's my domain, again going from smallest to largest. Now for the range, same idea. I'm going to go from smallest to largest, but what I'm going to do this time is I'm going to take a look at the y values. So starting down here, going up my y-axis, this point its y-coordinate is a -3. This point its y-coordinate is a -2. This point its y-coordinate is a 1. This point its y-coordinate is a 2. This point and this point have the same y-coordinate, but like we said before, we don't need to list it twice, just list the fact that it shows up. And so I'm only going to list that 3 once. Now, with the rest of these, determining domain and range is a little bit trickier, because what happens is if you take a look at this one and I try to identify its domain, well, there's a whole bunch of x's that are being covered here, a whole bunch of x's that are being established. For these points, its x value is -4. For this point, its x value is 0. For this point, its value is -1. For this one, it's -1. For this one, it's -2. This one's also -2. This one's -3, and this one's also -3. But notice, there's a whole bunch of stuff here in between. Whole bunch of stuff in between here. All of these x values are also getting covered. These ones as well, these ones as well, these ones as well, all the way up to here. So it's too difficult to list all of these points individually. It's much easier just to use an interval notation to list them. So what happens here is I'm saying all of these x's that are getting covered, they start at a -4 and they go all the way up to a 0. We've talked about interval notation before here. So from a -4 to a 0, and the idea is I need to decide, is that -4 a part of the domain? Is it an x value that's in that graph? Yes, it definitely is. It is included. It gets a bracket. We talked about that before. And also the 0, is it included? Is it a part of the graph? Yes, it is a part of the graph, so it as well gets a bracket. So that's how you identify the domain. The range, similar idea here, but I'm going to look at the y-coordinates. So I'm going to say, well, for this one, its y-coordinate is down here to -2. This one, its y-coordinate is +1. This one, its y-coordinate is 0. This one, its y-coordinate is a positive 1. This one, its y-coordinate is a positive 2. But notice that I got a whole bunch of y values in between here, whole bunch of y values in between here, and on up here, and on up here. So all the y's that are part of this graph are going to be from a -2 to a positive 2, and everything in between. So from a -2 all the way up to a positive 2, and yet again, is that -2 a part of the graph? Yes. So it gets a bracket. Is that positive 2 a part of the graph? Yes. So it gets a bracket. So these interval notations makes it a whole lot easier to identify your domain and range. Now, another thing that I will do to identify my domain and range is the idea, I call it the squishy game. I squish the graph. So in other words, if I need to identify the domain on this, I will squish this graph like this. And when I squish it, then that means all of these points through here are going to come down like this, all the way down through there. And all of these points are going to come up through here like this. And then all of the x's that are getting covered are from this -4 up to this 0. And that gives me my domain. And then when I need to identify my range, I will squish it again, but I will squish it along the x-axis this way. When I squish it along the, not x-axis, the y-axis, I'm sorry. When I squish it along the y-axis, then that means this point is going to come over here, and this point's going to come over here, but notice all of these are coming like this, and all of these are coming like this. And so all the y values that are going to get covered here on this y-axis are from a -2 to a positive 2, and that will give me my range. I can use the same idea on this graph, that when I'm looking at my domain and I'm squishing it on this x-axis, this is coming up here, this is coming down here, coming down here, coming down here, coming up here, coming down here. That identifies all those x-coordinates that we had listed. But notice these are individual points as opposed to continuous points. When they're individual, you can list them individually, but when it's continuous points, you need to list them as in an interval to be able to establish and say, listen, this is not individual points, it's continuous from here to here. That's what the comma means. And again, on this one, if I needed to identify my range, what I would do is I would squish it up along this y-axis. I would squish this over here, squish this over here. This one's already there on the y-axis. Squish these back like this and squish that like that. That identifies all of these y-coordinates that I have listed there. So that's another great way to identify your domain and range is with that, what I call this the squishing game. So here then on this graph, in order to identify my domain, what I'm going to do is I'm going to squish it up on this y-axis. And when I do, all of these are coming up through here. And all of these are going to come down like this. And then I'm going to look at this x-axis. I'm going to say what's getting covered. Notice that there's an arrow here and there's an arrow here, as opposed to this graph had endings to them. This has an arrow. What does the arrow mean? Yeah, that it's going on forever. So this is going to go on forever over here, forever over here. So as I look at this x-axis, what gets covered? Yes, absolutely everything gets covered. So everything from -infinity to positive infinity is getting covered. So my domain is going to be -infinity to positive infinity. And like we discussed before, infinities always get a parentheses. So parentheses on that infinity. Now, for your range, again, the idea is let's squish this thing up, but squish it on the y-axis. So when I do, all of this is coming over here, and the arrow means it's going to keep going down through the floor. This is all coming over here, and yet again, the arrow means it's going up through the roof, and I look at this y-axis and I say, okay, what got covered by all of that when it got squished up? Everything from -infinity all the way up to positive infinity. So my range then is going to be just the same from -infinity to positive infinity, and putting parentheses on the infinity because you cannot cap off infinity. Now on this last one over here, we've already identified that's a function. But let's take a look at that domain and that range. So the domain again is the x. So what I'm going to do here is I'm going to squish this thing up on that x-axis. This is coming down through here like this. Here's all the x-coordinates for that graph. Arrow means it's going on forever. All of these are coming down through here. Arrow means it's going on forever. Forever this direction, forever this direction. So here's my x-axis, what got covered. And yet again, it was -infinity to positive infinity with the parentheses around infinity because you can't cap it off. Now let's identify that range. And so again, on that range, I'm going to squish it up on this y-axis. All of this is coming over here, like this. And again, the arrow means going through the roof forever. All of these are coming over this way, like this, again through the roof. So here's my y-axis. Here's everything that got covered going on forever, so what got covered? Notice here it's not going down here. So this one is going to go not all the way down to negative infinity, but at 0, going up to positive infinity. And so that's how we get the range on that one. So as you can see, from 0 to positive infinity will be the range. Now the last task for us on this was to be able to find our x and y intercepts. So let's take a look at this one. Keeping in mind that my x-intercept is where the graph crosses the x-axis. Here is my x-axis. Where do these individual points cross that x-axis? You're right, they don't. And remember, by definition, it has to cross that axis. So if I don't have one that crosses the x-axis, I don't have an x-intercept. And it's okay to not have an intercept. You have to remember what the definition says. Now let's take a look at the y-intercept. Here is my y-axis, and I've got to figure out which of these points cross that axis. This one right here. And that is the point 0, 1. So that's going to be my y-intercept. Now take a look at this one. Continuous graph. Notice that when I'm talking about my x-intercept, here's my x-axis. Where's the graph crossing that axis? Right here. And that is the point 0, 0. And I also need to point out to you, do not list here. If you're listing none, do not list 0, 0, because that indicates that it is crossing there at 0, 0. On this one, you can see, no, nothing's crossing that x-axis at all. So don't list 0, 0, because that indicates that point. This one did happen. Now, the y-intercept, here's my y-axis. Where is this crossing that y-axis? Right here, at the same point. It is okay, not only is it okay to not have an intercept, it's okay for your x and y intercepts to be the same thing. Not a problem at all. So now let's take a look at this graph down here and identify its x and y intercepts. For its x-intercept, where is it crossing this axis? Right here at that point, which is identified as 2, 0. And now here is my y-axis. Where is it crossing this axis? Right down here at the point 0, negative 2. So there's my y-intercept. So now on the last one over here, let's identify again the x and y intercepts. X-intercept is where it crosses the x-axis. Here's my x-axis, crosses right there at 0, 0. And now for my y-intercept, crossing this y-axis, and it crosses right here again at 0, 0. And like I said before, it's okay to have the same point to be your x and y intercepts. All right, last two examples here. Doing the same thing on these two graphs. Identify whether or not you have a function, what is the domain, what is the range, x and y intercepts. Notice in this particular graph, it's a horizontal line. In order to find your function whenever you have a picture, remember the easiest thing to do is use that vertical line test. So I'm going to drop a vertical line, hits once, drop a vertical line, hits once, vertical line, hits once. I'm looking for this to happen, same x going to two different y values. When that happens, it's not a function. In other words, when that vertical line hits 2 times, I don't have a function. So that's not happening. That means, yes, this actually is a function. Notice in this one, when I drop that vertical line through here, it's hitting everywhere. So it is definitely hitting more than twice, which means no, this one definitely is not a function. Now let's take a look at that domain and range idea. Remember, domain is x. So what I'm going to do is I'm going to take this graph and I'm going to say, what of these x's are included in that graph? In other words, I'm going to squish this thing down on that x-axis all the way down through here. And notice that with these arrows going on forever, that means every one of these x's are included in that graph. All of these x coordinates are included in there. So if that's the case, then that means my domain is going to be from negative infinity to positive infinity. These are all the x coordinates included in the graph. Now, when I go to look at the range for this one, yet again, the idea of let's squish it up on the y-axis to see what y values are included in the graph. every one of these points here has a y-coordinate of -3. If I would squish it up on that y-axis, all these are coming back here and all these are coming back here to that point of +3. So my range has one single number in it. That's it. It is 3. Nothing more than that. Similar idea over here in terms of identifying domain and range. Domain, squish that thing up on that x-axis. What x values are included in this graph? Every one of these points up here has an x-coordinate of -4. Every one of these points has an x-coordinate of -4. So my domain has only one number in it. That single number is -4. My range, being that that's my y-coordinates, I'm going to take this, I'm going to squish it up on this y-axis. I'm going to say, on this line, what of these y values are included on that line? So everything, they all squish over to here. Arrow means going forever down, arrow means going forever up. So everything from a negative infinity up to a positive infinity is going to be included in that graph. So that's how you get your domain and your range on these two. Now, last thing, take a look at those x and y intercepts. X-intercept, remember, is where it crosses which axis? Yeah, the x-axis. Mathematicians aren't creative. So the x-intercept is going to be where it crosses this axis. Where does that graph cross this axis? No, it doesn't at all. And remember, it's okay to not have one of those intercepts. Now for my y-intercept, I'm going to take a look at this graph here. I'm going to say, where does it cross this y-axis? It crosses right here at 3. And remember, that's a point in the 2D coordinate plane, so I have to express it in coordinate form. The coordinates for that particular point are 0, 3. Now on this one, x-intercept, here's my x-axis. Where is this graph crossing that axis? Right here at -4. Again, it's a point in the 2D coordinate plane, so let's list it in coordinate form, -4, 0. And now what I'm going to do is find my y-intercept. Here's my y-axis. Where is this line crossing that axis? It's not. So therefore, our y-intercept is going to be none, because I don't have a y. It's not crossing at all. So this is how you identify your function, domain, range, x and y intercepts. Have a good day.